been dealing with JavaScript all day, and I needed a place to talk about that and also talk with other people about that. So I figured that we would make this meetup. The plan is to have it once a month. If you have anything you want to talk about, it can be anything related to computer science theory or a book or something other than, for example, Next.js. Maybe some other concepts. For example, hydration would be a good example of a computer science topic because that involves some algorithms and stuff like that. That's pretty much it. The next meetup will be 29th of October, yeah, I think, or 4 weeks from now, whatever that is. Anything else I need to tell you? We'll probably be in the Schibsted office again, unless someone else wants to host. They're more than welcome. So as I said outside, we will have 2 talks first, and then we'll go up and have some breakout rooms. And Ilya has some code if anyone wants to do some coding.
If you like the topic.
If you like the topic. And that's pretty much it. Yeah, so Ilya is gonna give the first talk about incremental computations.
Yep.
Yep. So go for it.
All right. Yep. It's actually not only the first talk of this meetup, it's also my first talk ever. So hold on to your rotten eggs and tomatoes until the end of the talk if it goes badly. We'll also be full of demos, so a lot can go wrong. But yeah, the topic of today is incremental computations. And yeah, first of all, I actually wanted to say how cool it is that we're gonna get together here. Actually, this is something that I was craving for a long time. I remember watching a documentary on PBS. It's kind of like American alternative to NRK. And it was a documentary where they took scientists from all the different branches and then they paired them and they let them explain to each other what they do and why is it fascinating. And I remember I thought, geez, it's gonna go horrible. It's like an ivory tower of sciences, you know, the chemist says, oh, this is so cool because, but then physicist, yeah, but it's all physics, and then mathematician, yeah, but it's all mathematics, and so on and so forth, until category theory or something like that, where they say just pitch please. But reality was quite different. Even though they were so far from each other on the tree of knowledge, they could explain to each other, like a linguist could explain something to a theoretical physicist about their research, and they managed to convince each other that it's fascinating, and it left quite an impression on me. It let me know that you can express something really interesting and it's universally interesting. You just need to know about it. And we're so lucky to do our work in computer science that is so branched out that we can also share this kind of tidbits that are actually super fascinating. You just need to know about it. And so in this sense, I'm gonna try to convince you that what I'm passionate about, incremental computation, is also pretty cool. So right now I work at a company called Murkan, and we do a lot of data processing for markets and games. And I remember when I just started working in the company, I thought, it's so cool. Processing the data, much more fun than doing business logic, shopping carts and that kind of stuff. But the same problem, it was solved in the company before I came, was popping up again and again. Let's say you need to compute something, but at any given point in time, there's just a small tidbit of data coming, and then you need to recalculate some partial view of your data. And it's kind of hard to do it manually. It's kind of dumb to do it everything from scratch. And so you need to find a good approach to do it smart. And it was about the same time when I was getting interested in functional programming, and I was, thinking, oh, probably I can slap a monad on this. And spoiler alert, you can actually do that. And the library that we're going to use to cover this topic uses monadic API. But the general concept that I kept in my head is something akin to an Excel spreadsheet. I genuinely believe that this technology was decades ahead of its time. The fact that you can specify some computation and then change just one number and it magically recomputes wherever you want, to me is still a little bit of a magic. Especially if you take into account that if you modify just some part of your data, only that data that depends on that data will be recalculated. So, first of all, this process is reactive, which means that the data updates automatically. We do not have to query the data. And the second insight is that we only recalculate what needs to be recalculated. And so this is something that I kept in my head, but I couldn't find the proper abstraction for this for quite some time. And at first, I stumbled upon observables or reactive extensions. And that sounded very similar to what I wanted to do. It is reactive, it is in its name, reactive. And so I thought maybe this will solve my problems. So now I need to figure out how to turn off mirroring, because I cannot see anything otherwise. Oh, there we go. Yeah, by the way, quick show of hands. I hate when they do it in the talks, but I promise this will change the course of this topic. Is anyone familiar with ML family of languages such as Elm, F#, and so on? Okay, well, I feel like it's about a half. Would be better if there was more people like that, but we'll try to cover some of the topics that are important to understand as we go along. So I'm actually gonna open two views of the same program. I just need to zoom it in. Is that legible?
Yes, sir.
Okay, cool. So on the left side, we have a small program expressed in C#, so it should be fairly familiar to most of you who's familiar with Java or JavaScript or any other, earn your money with it language. And on the right side is F#, which is similar to Elm and ML and so on. And so I put them here so that you can see the similarities and just some differences in the syntax. Maybe we could turn up those slides so that they don't reduce the contrast of the text. Or maybe it is fine.
I think it might be complicated.
If you switch to light mode.
Yeah, light mode is probably better for a projector.
But is it good?
Oh.
Sorry?
How is it?
Okay, I know I can do this.
Yeah, it's actually.
Perfect. Yes. So, the idea here is I want to create a reactive addition. So I create two, what we call cells with data, just like in the spreadsheet that I showed you before. There are two cells, cell A and cell B, and we express our cell C, or in this case we call it plus, as the addition of the two. And so what you do, how you do it in reactive extensions is that you define something that is called a subject. There's a lot of complexity, behavior, subject, and so on. We're just going to leave it. Subject is just a cell that you can assign a value to, and when the value changes, it propagates that change to everyone who is subscribed to it. And so we create two subjects called A and B, which are like cells in Excel. And then we define our plus operation. We use what the functional languages call combinators, just the ways to combine two different things. In this case called combine latest. It will take, it will take the latest available value for A and B, combine them in a list, and then we can map over that list and do whatever we want. So let me actually refer to this here. And I inserted this console log so that we know when this expression is reevaluated, we see the console log printed. So we first make it into a list. This becomes a list of integers. We know that there's going to be just 2 integers. So we add them up, and the return type that we get is observable of integer. Perfect. Now we can subscribe to it, and while subscribed to it, we can just continue printing to the console. So let's see what's going to happen. If we run it now, first we can verify that if we don't make any subscriptions, then nothing will be printed. So that's great. It means that if no one is listening to our computation, then nothing will happen. But then, as long as we have at least one subscriber, when it subscribes, it will go to this computation and it will reevaluate it. So we see that this is printed first, and then the subscription prints the result, which is 3 in this case. Now, as I said before, we can go to one of our subjects and change its value. So we change the value of A to 100. And so as you can expect, now we'll see first this console log that will say that the value has changed. It will reevaluate it, and we'll see 100. So we see that it executed first, then this print line appeared, then we actually executed the summation, and the result is 102. So that looks great. That looks exactly like we wanted to achieve with the Excel spreadsheet-like abstraction. But now let's see what happens if we refer to the same cell again in this scenario. So now you can see that this operation was executed twice, even though we modified, or maybe let's do it one at a time for better understanding. Again, if we don't change the value, we just get the result as we expect, just the result of summation, just the subscription, and so 1 plus 1, oh yeah, we refer to A twice. So now when we try to change the A to 100, it actually executed twice. So we know that we don't want this work. We know that we changed this value and we needed to recompute it just once, but our algorithm did it twice. And so we see that we just did extra work. So that's not good. So what we see, the nice things is that observable gives us a notion of a cell, some storage for data that we can change, and that change will be reactively propagated forward throughout our computation graph. And you can imagine this computation as the graph having 2 leaf nodes, A and B, and one final leaf called C or plus. Observable itself provides a lot of useful combinators for all kinds of stuff. We got a couple of insights, some computations can be skipped if no one is listening, and that is great. So now we make our computations only if there is a demand for them. And also, we notice that to modify the input and combine it with the graph, computation graph in general, it has a separate type. In this case, it's something called subject. But it has a lot of downsides. It has a very complicated API because it introduces time, and actually reactive extensions are not used for this specifically usually. It's for tracking mouse clicks and so on and so forth. And those of you who work with anything that involves time, you know that it makes everything about 100 times more complicated. The streams themselves with the data can end, and you have to account for that. So if you think in terms of pure functional programming, it's an additional effect that you have to keep track of, that you have to think about. And as we saw, there's no native way to avoid double computation. And so what we just saw is similar to this computation graph. Let's say that we have an initial cell called A, and then two cells, B and C, that both depend on A. And in our example that we just saw, we just had A's instead of B and C. And then we had some result, in this case D, that depends on those cells B and C. And we saw that in reactive extensions, it's not possible to, well, unless you introduce huge hacks, it's not possible to avoid this double computation. And the reason for that is because in reactive extensions is just a way to chain callbacks. In other terms, this graph, this DAG, with reactive extensions, we traverse eagerly. We go depth first. We change A, it propagates the change to B, but then because B changed, it has to propagate the change to D, and then we evaluate the D. And that's why we saw 100 plus 1. But then it goes, and A knows it has one more subscriber, and it goes propagate the change to C, and then it propagates the change to D, and then finally we get the consistent result. But while we were doing this, we actually reported inconsistent results. Like in our example, when we changed 1, we didn't expect to see 101. We wanted to see just 200. So, does anybody want to try to guess how we could solve that? So this is a DAG. We went too eagerly. So maybe instead of depth first search or traversal, we could go with breadth first traversal. And in this specific case, that would work. If we change A, it propagates the change to B, and the B recalculates itself. And then it says, all right, hold your horses. I have to report it to C first. Propagates the change to C, and now we go to the second level, and now others propagate their changes. But this assumption breaks down as long as you have unbalanced DAGs. In this example, you can easily convince yourself that we will not arrive to the computation D at the same time. We'll have the same exact problem. So, how would we solve this? And the answer to this is to break down our computation in 2 steps. The first step, we'll go through the graph, we'll mark everything that was outdated or potentially outdated. We have enough data to suspect that it's outdated. We'll put all of our computations in a priority queue, and then we'll start popping from that priority queue and recompute everything that has changed. Or you can imagine the first path will go like this. If we change A, it will go depth first, it will mark B as dirty, it will mark B prime as dirty, it will mark D as dirty, and then it will mark C as dirty, and it will mark D as dirty as well. And then when someone requests for the data on D, they'll know that 2 of their inputs, both of them, are dirty, so you have to recalculate them. And you can imagine if you had another branch of the graph that did not start at A but ended at D, and we only changed A, that part of the graph we will not recompute. So we saved potentially a lot of compute time. And now we'll jump back to our codes. Is everything clear so far? Okay. I think it's fine if you ask questions, if they arise. Okay. But now we move on to something called adaptive. And this is actually one of the implementations for incremental computations. We'll cover the history of it and the other names a little bit later. But for now, this is an implementation of this in .NET ecosystem, specifically in F#. And some guys in Germany did it for graphics intensive applications. So just like before, we declare two cells. In this case, it's called cval, or changeable value. And then we combine them and get as a result something called aval, adaptive value. And so, just like before cval, just like before in reactive extensions, a subject was a case of an observable, of iObservable. Cval, or extends iObservable. Cval extends adaptive value. And the only difference is that you can manually change and modify the value of C value. And for adaptive values, you can only compose them together. And so we do exactly the same thing. We get two cells. We inject our print statement just so that we can see when this thunk is re-executed. We add up the two values that we passed in our function. We use the map2 combinator. So for those who knows, yeah, we can have a look at the type of this thing. So it takes a function called mapping that takes t1, t2, and returns t3. And then it takes two values, a val of t1, a val of t2, and it will return an a val of t3. So if you're not familiar with functional programming, you can think of this as I don't know, but yeah. So you can think of it as it knows how to get the value outside of the two cells of two a vals, and then smash them together and get one cell with both of them. And we just need to provide a function that will know how to combine the two values that we got into one value. So the simplest example, like before, you can think about this mapping function as something that takes the two values and pops them in a list. And this is exactly what we got in the reactive extensions example. And the type of the thing that we get back is a queried function that will take one a value. We could have casted it here. One a value, second a value, and it will return the sum of them because this is the thunk that we provided inside. And so now we apply the both of them. Okay, now you can think of us coming from the other side of the graph and forcing the computation and seeing what's the result of our sum. It's going to be our first test. So if we run this, as you can see, we force our computation twice, but the thunk that we put inside is executed just once. So it tells us that the computation was cached, which is great. We didn't have to do it twice, even though if we were to make the summation with just a regular function, we would execute it twice and we would lose some CPU cycles. So another helper function is something called, something called add marking callback, and this is just a callback that we add to the last node of in our computation graph. That will be invoked when it was called the last time, being marked as dirty. And if we run this real quick, we see, okay, I'm not sure why it wasn't called. Oh, because I didn't mark anything dirty yet. Sorry. Now we're gonna mark it dirty. Just like before, we're gonna set the value of a to 100. So here we announce it, and then we actually do it in adaptive, F# adaptive. You have to use a transaction. So you open a transaction, you can do as many modifications as you want, and all of them will be flushed as one. And now if we do this, all right, so we executed our function, we printed it twice, then, oh, I forgot to do this, sorry. I actually didn't ask for computation. So we, summing 1 and 2, we can see that we do it just once. Then we set the value of a to 100. Our callback is called. The value is dirty, so now it's time for us to call the summation, and now we can see that it was called just once. And we can verify it again if we refer not to A and B, but to A and A, just like in the previous example. And in the previous example, we got an inconsistent result of 101. But here, everything is consistent. Once we set A to 100, we get just one result of summing 100 and 100, and it was 200. All right, so this already, I'm not sure how easy it is to extrapolate from here, but you can imagine to creating as deep computation graphs as you want with this, and then modifying your inputs once and only getting the outputs efficiently calculated, finding the optimal path for calculations, and marking and recomputing only the things that you want. The only thing that, and we avoid double calculations like in before, and we don't calculate anything if someone is not subscribed to our changes, if someone didn't force the actual calculation. The only eager part that we do is marking things dirty. And the one thing that we're missing is our ability to create dynamic graphs. So right now, once you created your computation, you are not able to change it at runtime. But it would be nice to have something like this. Let's say we define our cell X as dependent on cells A, B, and C. And if A is greater than 0, then return B, and therefore track B, because B is this reactive value, reactive cell. And otherwise return C. And our expectations is that if we have initial value of A greater than 0, and we do return B, then when C changes, we don't want to redo our calculations, because we're not actually interested in this. We're only interested in B. So we want to avoid that part of the calculation of the graph. And you know, it's easy to imagine, oh, well, why do I need to do this with plus and minus and if? But of course, this is just a toy example. And fetching something from the memory is 100 times more expensive than actually doing the summation. But you can imagine that this C, expression C, could be very expensive, or it could be the graph itself that is very nested and so on. And so we'll go back to our example. The next one. Just like on the graph, we define 3 cells, A, B, and C. The cell A is 1, 2, and 3, respectively. Then we define our calculation. And for that, we're going to use map 3. It's just like map 2, but with 3. No surprises here. And we define calculation as such. Then we pass our values, A, B, and C. And we're going to do basically the same. We're going to invoke our calculation twice, make sure that it only calculated once. We'll register a callback that will tell us when something is dirty. Then we'll set the value to 100. Value of an A to 100. Well, that's not terribly interesting. Okay, I'm just going to skip it if you don't mind. It's not that interesting. Instead, we'll just jump to this. Remember how we said that we don't want to redo any calculations if the value of C is changing, because we don't return it. We're not interested in what's inside. But what we used so far is the applicative, and we do make a subscription to the C, and we can verify it by running this. Oops, that was the wrong one. Sorry. So here you can see that we changed the value of C, but our computation was still marked as dirty. And as I alluded to before, it's because we used the map function that actually eagerly requests for values, for all the values that we passed inside, even if it's C and even if we didn't use it inside. And so what we need instead is a function called bind, and this is what makes our API monadic. Bind makes this a monad, and we can specify our computation. We can have a look at the signature of this. So it takes a function of mapping that will actually return an A value of T2, and when we pass T1, it will return us T2. And so with this, we can specify our calculation that will only make the subscription to the right cell, depending on the value of A. And if we rerun it now, you can see that we changed the value of 5, but nothing was marked dirty. So our calculation, this callback, oh wait, I forgot to insert it inside, I'm sorry. But because nothing was marked dirty, we just got the cached value when we refreshed it again. So we did not do the whole calculation over again. And so at this point, we're actually able to create any computation graph that we can imagine, and it will be recomputed efficiently. If we're not interested in something, even if the condition is dynamic, it will not be done, and we'll do the maximum saves. But algorithms are good. What about the data structures? Can we do something here? And I ask you to consider a data structure that we'll call an append list. And we're interested in the function max of this append list. So if it's a list of 1 to 3, an append list is just a list to which you can only append new values. You cannot change anything previously. You cannot delete anything from it. You can only append to this. And so we're interested in the max function. So the signature of such a function is if we give it append list of t, it will give us the maximum value of t. And just assume that the t has the implementation of comparable. Let's say it's an integer, like in all the examples before. So you can easily convince yourself that if we do the from scratch algorithm, so if we have a list 1 to 3, we ask what's the maximum value, like in the regular programming language. The complexity of such a function will be O of n. It will be proportional to the number of elements in the list. And then if we add the value of 4, we'll get the value of 3. But if we add the value of 4, we have no other options other than to rerun the whole computation again, at which point the computational complexity will be O of n again. But we know that there's a better way to do that. We know that we just need to track the biggest value so far, and when we append the new value, we just need to compare it to the value we've got so far. And so we know we can do it in O of 1 instead of O of n. And this actually doesn't exist in the library, but I just invite you to imagine it. Imagine that we have an A append list, an adaptive append list with the max function. And then the signature of such a function would be given an A append list, it will return us an A value of such a value, of maximum value. And when we change something inside of the A append list, it will be proportional only to the size of the change that we made, to the size of the delta. So if we append just one value, it will be just one comparison operation. If we append m values, it will be O of m compared to O of n plus m if we were doing this from scratch. And so this algorithm we would call from scratch implementation. And this algorithm we would call incremental computation. And the core idea of incremental computation is to build such a computation that is that gives us either that has computational complexity either proportional to the change that we make, which is the ideal case, or in some cases that provide us with asymptotic improvement. So let's say instead of O of n, we would get O of log n, which would be the case for just a regular list, for example. And another very important property of incremental computation is that we are able to compose such values. So if we have some computation, we can compose it with other computations, and so on and so forth. And this is only relevant for the library that we've been talking about so far, F# adaptive. We've looked at the C value of t, and it extends A value of t, which just propagates the change. And the combinators are located under A val of map. But you can also get access to an implementation of list, to implementation of set, to implementation of map. And so you can imagine that you can build pretty much anything with this. So we get enough tools to build pretty much any program, and then it will be doing the least amount of possible computations, which sounds really, really cool to me. And the most important part is that we don't have to think about, oh, how do I compose all these little tricks here and there when I was caching values. It will be all done for you. We just need to do it once. And this is another very important property of incremental computations. We want to think about our algorithms as from scratch algorithms. So just a regular, list.max, instead of, oh, I need to keep track of what was the maximum so far, and if I append, blah, 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 blah. We just think about it as if we do it once, and we can rely that the result will always be consistent when the changes to the input of our algorithm is just a little bit. And this is, by the way, a great way to test it. This is how I do it sometimes. Alongside of whatever algorithm I'm trying to incrementalize, I just do a dumb algorithm with for loops and whatnot, and I just make sure that the results are the same. And so this would be the mental model for incremental computation, where I is the input, and O is the output, and P is the sum computation. If you don't look at the dotted lines, when we change our input just by a little bit, by delta I, we can go what we call from scratch. We can just apply the full P to our I of 2 with the change, and then get the full value. So that was the O of n of maximum in the list. Or we can construct our computation P, just thinking about the P itself, such that it knows how to derive delta P, the incremental algorithm itself. And then we change the I in some small amount, it will know automatically how to apply delta, how to derive delta O, and apply it to O, and apply it efficiently. So you can think about incremental algorithms and have a mental model, or where can I use them in several ways. As we talked, it's performance optimizations. It can and often does give us asymptotic improvements. It is also memory versus CPU trade-off, because we cache a lot, but instead we spend less time actually doing our computations. It's a way to chain and propagate the minimum changes in our algorithms. And this would be important if you wanted to serialize the changes between your different stages of your algorithms, for example. You can also look at it as an automatic cache invalidation mechanism. This is actually what I heard the guys from Aardvark, the guys who wrote this F-sharp adaptive library, usually refer to. And so, what are the interesting uses for this? This is a screenshot from Strangeloop. I assume this crowd watches Strangeloop. If you don't, you should. Really great talks. Jane Street, one of the trading firms in the US, made an implementation of incremental algorithms themselves. And surprisingly, they didn't use it for trading. Instead, they used it to build data-driven UIs. Just like in the first screenshot in my presentation, they have UIs with lots and lots of rows. They need to update efficiently because a lot of money depends on it, and they want to render it in regular browser. So we can think about our updates to the DOM, in a regular loop of our front-end frameworks. As we have a model, we generate virtual DOM out of the model, and then we update, then we create our DOM. And that's always it's always the case on the first run, when, let's say, we just received our model, we just created our model, and we paint the first DOM representation. And then the simple way, like if we just don't look at the arrows between and just we update our model and we get model prime, we can go from scratch and just forget about VDOM we had so far and instead create VDOM prime and then remove everything from DOM and repaint the whole DOM. Obviously, this is very, very expensive. And so that's where people came up with the VDOM. That's why it's in the middle. Instead, they started, when we have model prime, we generate a new VDOM prime, we diff them manually, and we only apply the changes to DOM to get our DOM prime, the minimum amount. But the problem here is that arrow, the leftmost vertical arrow, does not exist in most systems. And you have to generate the whole virtual DOM from scratch and then diff them. But what if we generated our models such that they know themselves how to track the changes efficiently, and we don't need to spend time to generate the new VDOM prime? Then a lot of the time on the front end could be spared, especially if your applications are very data intensive, if you have hundreds of thousands of rows on the front end. Another interesting way to think about it is to use it for database view maintenance. Those of you familiar with databases may know that materialized view is like a special unicorn that everyone wanted to achieve for decades, but no one quite got it. But there's a company called Materialize with Frank McSherry, who implemented like an incremental computation engine in Rust, and he started a company with this called Materialize. And what they do is that you can get incremental streaming joins, which, to my knowledge, no one else can do. So, very, very cool company. And you can see they even have computation graph down there, just like we were drawing so far. Incremental computations can be used for compilers. Could be interesting for those of you with your own programming languages. Anyone? So for example, the F-sharp adaptive, there is some initiative to use it for compiling F-sharp. Just saw it on Discord. And also FS autocomplete. It's a tool for IDEs. It's also used in Vim for tooling for F-sharp. The creator is trying to use F-sharp adaptive right now to speed up the process. Okay, that's pretty much it. If you want to read more about it, you can check like the first two is more academic stuff. Umut Akar is the guy who started it. If we don't talk about dynamic programming, which you can also think about as incremental computation, just not general enough. Umut Akar started the whole thing and called it self-adjusting computation. He still does some research to make it parallel, fully parallel, as far as I know. But he has a website and you can go and read some papers about it. Matthew Hammer is a student of him, or I don't know how to say it. Umut Akar was his advisor. He created a language called Adapton, which is based on incremental computations fully. Then he did some research and did Adapton with names. Didn't quite figure it out yet. Fungi, another language. And he also did some additional research on that, which you can also Google and read. F#.data adaptive is a part of FS project from guys in Germany company called Artfark. They actually do graphics intensive applications. They do a lot of cool stuff, and this repo has way too few stars, so if you have a chance, please go and give them a star. And also in .NET, Nayab, I don't know how to pronounce it unfortunately, by the same guy, Frank McSherry, who later founded Materialize. He used to be a part of Microsoft Research. He did some work there, and that library is public as well on GitHub. And in OCaml, there's Incremental that we talked about before, Incredum, that allows you to incrementally change your model and, well, basically that screenshot from Strangelove that I showed you. And they also made another abstraction called Banzai for better composition of your components. It's a little bit harder to read. To me, OCaml has too many squiggly lines and weird symbols. And also, they're pretty much the only users of OCaml, and it's hard to build. But for those of you who are brave, you can give it a try. All right, that's it for me. Thank you very much.